Good afternoon, everyone. For this afternoon session, the first speaker is Professor Katsuyuki Naoi about generalization of the extended T systems by a strong duality data.
Thank you for introduction. And first of all, I'm very happy to join such a wonderful conference and have a chance to give a talk. So I'd like to express my sincere gratitude to the organizers. Thank you very much. And now I will start. And the plan of this talk is as follows. In the first part, we will recall the Mohin-Young's externality systems, which is what we would like to generalize in this talk. So this also appeared in the previous talk, but let me give a detailed review again. In the second part, we will recall the notions of strong duality data and affine Caspian modules, which are fundamental notions to state our main theorem. So the goal of this talk is to introduce the theorem, which says we can generalize the Mohin-Young's externality systems using these notions. Then we will state the main theorem, and if time permits, I will give a sketch of the proof. And let us prepare some notations. So let G be a complex affine real algebra. And let U-G denote the associated quantum affine algebra. And we assume that its index set is from 0 to n. And we further assume that the parameter Q is not the root of unity. And as you know, this is an associative algebra. And it is defined as a kind of Q deformation of the universal enveloping algebra of affine real algebra. Okay. And in this talk, we only consider finite dimensional U-K modules of type 1 precisely, but you don't care this seriously. Anyway, we consider finite dimensional modules only. And we denote by CG the category of finite dimensional U-K modules. Then this category has a quite rich structure. For example, since U-K is a Hopper algebra, we can define the tensor product of modules. And moreover, there is a trivial module. Then by them, this category has a monoidal category structure. So in particular, by considering the tensor product, we can define a ring structure on the Grothendieck group. And we call this ring the Grothendieck ring. And moreover, this category is rigid. Namely, each module has a right dual and a left dual. And we denote them by dm and d inverse m, respectively. And it is an important and quite difficult problem to study the structures of tensor products of simple modules, such as Jordan-Helder series. This problem also appeared in the previous talk. And in this talk, we will treat this problem mainly. Okay, and let us recall this famous theorem by Chari and Presley. So the isomorphism classes of simple modules in CG one-to-one correspond to the Drinfeld polynomials, namely n tuples of polynomials whose constant terms are all one. Then using this correspondence, in this talk, we denote a simple module using monomials in these infinitely many variables. And this is an example. So if we consider this Drinfeld polynomials, then we denote the associated simple module under this correspondence by this notation. So note that these first parameters denote the numbers of polynomials, and the second parameters denote the powers of the roots of the polynomials. So 1 minus 2, 1 minus 2, 1, 2, 1, 2, 2, 3, 2, 3, 2, 7, 2, 7. Anyway, in this talk, we denote simple module using this notation. And of course, by this notation, we can express some of simple modules, but these are enough for our talk. In particular, a simple module associated with a degree 1 monomial is called a fundamental module. Now, before recalling the XNT systems, let us recall the T systems, which are origin of the XNT systems. The T systems are certain relations in the Grothendieck ring of CK for the tensor products of Kiro-Lattice modules, or KR modules for short, for general affine G. So KR modules are simple modules of this form. And this is an example of the T systems for untwisted and simply lessed affine G. Note that these are all KR modules. So T systems are relations in the Grothendieck ring satisfied by the tensor products of KR modules. Then, motivated by this, in types AN1 and BN1, Muhin and Yang introduced in 2012 similar relations called the XNT systems for prime snake modules, which we will recall in the next slides. In these types, XNT systems contain all T systems, and there are many other relations. Okay, now let us recall the T systems. But for simplicity, in this talk, we will only consider type AN1. So this is the linking diagram of type AN1. And we denote by Jn the subset of this subset of the product of the sets from 1 to n and the integers. And here we plotted elements of Jn on a plane when n is 5. So 1, 1, 1, 3, 1, 5, 2, 0, 2, 2, and so on. And first, as a preparation, we consider the following slightly combinatorial definition. So a sequence Xi of elements of Jn is called a snake if these conditions are satisfied. Namely, for each pair of neighboring elements, or each pair of neighboring elements, this inequality holds. And this inequality is explained pictorially in this way. So if Ik is this black vertex, then this inequality says that this blue vertex must be, so I dash K dash must be placed in this blue region. And we also define a prime snake. So I think this notion is the same with connected in the previous Matthew's talk, but we call this a prime snake. And this is defined by adding these inequalities. So these inequalities are explained pictorially as this. So if Ik is this black vertex, then I dash K dash must be placed in this red region. So snake is a sequence of elements of Jn ordered from right to left, ordered from right to left, and each neighboring vertices satisfy these conditions. So this is an example of a prime snake. And I think you can see why such an element is called a snake. So this is like a snake. Okay, this is like a snake. And for a snake, by considering the corresponding monomial, we can consider the associated simple module. And we call this module a snake module. And for a given prime snake, we define two other snakes called the neighboring snakes. And this is an example. So I hope that you can guess how to define neighboring snakes from this example. So if these black vertices form the given prime snake, then these blue stars form the higher neighboring snake. And these red stars form the lower neighboring snakes. Anyway, given a prime snake, we define two snakes following some rule. Then the following theorem is proved by Milen and Yang. So a snake is prime if and only if the associated snake module is prime as a module. Recall that we say a module, simple module is prime if it does not have non-trivial tensor decomposition. And this second relation is called the externality systems. So they prove that for each prime snake xi, this relation in the Grothendieck ring holds. So note that this monomial is obtained by omitting the leftmost one, and this is obtained by omitting the rightmost one, and this is whole snake, and this is obtained by omitting the leftmost and rightmost ones, and these are neighboring snakes. So they prove that for each prime snake, this relation holds. And moreover, they also prove that two tensor products in the right-hand sides are both simple. So in particular, the tensor product in the left-hand side has length 2 Jordan-Helder series. Okay, these are called the externality system. And so in this example, the relation is written explicitly in this way. So for example, this comes from 513, 511, 48, 35, 22, and we omit the leftmost one, and so on. And I will give some remarks. First, if we consider a straight snake, so namely a horizontal snake, then the external T systems recover the original T systems. So in type N1, external T systems contain all T systems. And as said before, Milen and Yang also proved, also obtained type Bn1 external T systems. And the relations themselves are quite similar, but in type Bn1, the conditions of snake or neighboring snakes become slightly more complicated. And because of time limitation, I will omit them. And for the proof, Milen and Yang used the theory of Q characters. So Q characters are a fine analog of characters. And briefly to say, they prove this relation by calculating the Q characters of both sides and by showing that they are equal. Now, finally, it is expected that these are mutations of cluster algebras. So it is known that the Grothendieck ring of Sigue has a cluster algebra structure. And then it is quite natural to expect that these external T systems come from the mutations of cluster algebras. So mutations are important relations appearing in the cluster algebras. But as far as I know, this has not been proved so far. So, it might be interesting to study the relations with cluster algebras in the future. Okay, so these relations in the Grothendieck ring are called the external T systems. And now I will mention the goal of this talk. In this talk, we will introduce our main theorem, which says that the same relations also hold if we replace the snake modules with simple modules of this form. So we show the relations which is obtained by replacing these snake modules with other modules of this form. And here, HD denotes the head, namely the maximal semi-simple quotient of these tensor products. And these modules, Sj, are affine caspital modules, which are defined from a strong duality datum. And so we will recall these notions in the next part. And it should be mentioned that these notions are introduced by Kashiwara, Kim, O, and Park. So all the results in the second part are due to them. And before recalling these notions, let us recall an important invariance defined on the pair of simple modules. So for simple modules M and N in Ck, an isomorphism from M tensor N to N tensor M doesn't necessarily exist. So they may be isomorphic, but may not be isomorphic. But if we consider these modules over the field of rational functions, then it is known that there always exists an isomorphism. So note that we consider a module over the rational functions. So if we change the base field, then it is known that there exists an isomorphism. And by normalizing suitably, we obtain a canonical one, which is called the normalized R matrix. Then we consider the following definition. So for simple modules M and N of Ck, we denote by delta Mn, which is a non-negative integer, to be the sum of the degree of the pole of this normalized R matrix at z equal 1, and the degree of the pole of this normalized R matrix at z equal 1. So note that here we consider Mn. This is Nm, so they are different. And so they are opposite direction in some sense. And you may think that this definition is quite technical, but actually this is important and quite useful invariant in the theory of finite dimensional modules of Kuiper-Hecke algebra. Quantum affine algebra. Quantum affine algebra. So, for example, the following useful facts are known. So, suppose that one of M or N is real. So recall that we say a simple module is real if the tensor product with itself is still simple. So under this relatively mild condition, these facts are known. So the value of delta is 0 if and only if M tensor N is simple. And moreover, M tensor N and N tensor M is isomorphic. And moreover, if the value of delta is 1, then m tensor n is no longer simple, but it has a non-trivial short exact sequence with k and l being simple. So in other words, if this condition holds, then m tensor n has thanks to Jordan-Herder series. So intuitively, this invariant measures how far m tensor n is from being simple. And this invariant is quite useful and important in the theory of finite dimensional Yuki-Dashige modules. Okay, now let us recall the definition of strong duality data. And so here we fix a Cartan matrix C of finite AD type. And note that this Cartan matrix is irrelevant to the type of K. So recall that in this talk, we fix a quantum affine algebra, Yuki-Dashige, but we can take independently from, we can take this Cartan matrix independently from the type of K. So for example, if we consider type Bn1 quantum affine algebra, we can take type An or Am or Dm or and so on. Anyway, and we consider the following definitions. So a family of real simple modules, D, consisting of simple modules, Li, is called the strong duality datum associated with the Cartan matrix C if these conditions are satisfied. And recall that this D denotes the right dual, and D inverse denotes the left dual. So this module is obtained by taking the duals repeatedly from Li. And then these conditions say that the values of delta are 0 or 1. So note that since we consider finite AD type, this minus Cij is 0 or 1. So these conditions say that the values of delta are 0 or 1, and 0 in many cases, but sometimes 1. And they are determined from the Cartan matrix. And so you may think that this definition is complicated. And in fact, for this talk, you don't have to remember this definition itself, but this proposition is quite important for this talk. Sorry, this? Oh. Yeah. So here, yeah, so they are opposite. Sorry. So I didn't notice such a critical mistake. And I used this slide in the past conference, so I didn't notice that. Thank you very much. So this condition is might be incorrect. So please refer the original paper. Anyway, there is some conditions, but you don't have to remember this. So this proposition is important. So if a strong duality datum is given, then there is a unique Z-algebra homomorphism phi d from this quantum group to the root and equal ring of Ck. So this is an integral form of the dual of the negative half of the quantum group associated with C. But anyway, this is a kind of quantum group, and there is a unique homomorphism, and such that it maps a Chevalier generator to the class of Li belonging to the D, and it maps Q to 1. And the next statement is also important. So moreover, this phi d induces an injective map from the upper global basis to the isomorphism classes of simple modules in CK. So upper global basis is an important basis of the quantum group. And this phi d maps an element of upper global basis to a simple module. And this map is injective, but not surjective. And although the construction is not used in the sequel, let us recall briefly how to define this phi d. This phi d is defined by the composition of the following two homomorphisms. The first one is this isomorphism from the quantum group to the Grothendieck ring of the finite dimensional graded modules over Kuiper-Hecke algebra. So this result is obtained by Kovanov-Lauder and Ruquier, which says that the Kuiper-Hecke algebra categorifies quantum group. And the second homomorphism is this. And then this is induced from the quantum affine Schubert duality functor from the category of graded modules over Kuiper-Hecke algebra to CK. So if a strong duality datum is given, we can define a distinguished functor called the quantum affine Schubert duality functor between them. And since this functor is monoidal, it induces algebra homomorphism. Then by composing these two homomorphisms, we obtain this phi d. Next, let us recall the definition of affine Caspian modules. So let D be a strong duality datum. Then we can define an algebra homomorphism of phi d, and it maps element of upper global base to a simple module. And here we fix a reduced word I of the longest element of the while group associated with C. So note that n denotes the length of the longest element. Then for each j from 1 to n, we denote by f beta j an element of the quantum group defined in this way. So here, Ti denotes the Lustig's braid group action. And so Lustig's braid group action is an analog of reflection. So this is an analog of a root vector, since we consider the image of a Chevalier generator under the reflections. Then by normalizing suitably, we obtain an element of upper global basis. And this is called a dual root vector. Then we define affine Caspian modules as follows. So affine Caspian modules are an infinite sequence of simple modules parameterized by integers. And the definitions are as follows. For each j from 1 to n, we define Sj as the image of this dual root vector and the phi d. So phi d maps element of upper global base to a simple module. So we can define this. And then, so for this finite j, we can define Sj. And then in the second process, using this second process, we extend the definition to all integers. So namely, we define Sj plus minus n to be the left or right dual of Sj. So by repeating this process, we obtain all Sj for integer j. So affine Caspian modules are infinite sequence of simple modules determined from a strong duality datum and a reduced word. And this is an example. So we consider type AN1. So let D0 be this finite set of fundamental modules. Then we can check that this forms a strong duality datum of type AN. And we take this special reduced word. Then by definition, S1 is the image of the Chevalier generator F1 and the phi D0, and this fundamental module. S2 is the image of this dual root vector and this fundamental module, and so on. And Sn plus 1 is, by definition, the left dual of S1, so this fundamental module. And so, and finally, we can check that in this case, in this special case, affine cuspidal modules are the same with the fundamental modules. So in this sense, we can see that affine cuspidal modules are generalization of fundamental modules. Here, for later use, we define a bijection phi from this set to the set of integers in this way. So since these sets coincide, we set phi ik to be an integer corresponding to this fundamental module under this coincidence. And we will use this bijection later. But if we take other data, then we obtain other affine cuspidal modules. So for example, if we take this set as a strong DI datum and I0 is as above, then in this case, affine cuspidal modules are no longer fundamental modules. Okay, now I will state the main theorem. And the setting is as follows. So let D be a strong DI datum of type AN. And in this main theorem, we consider only the special reused word. So this is the same with the previous slide. So in the main theorem, we can only consider this special reused word, but we can take an arbitrary strong DI datum of type AN. And we consider the associated affine cuspidal modules. And then, so in order to state our main theorem, we have to change the labeling. Recall that affine cuspidal modules are parameterized by integers, but in order to state our main theorem, we have to change the labeling from integers to this set, Jn. So we set Jn to be this set, and we define Sik to be this affine cuspidal module for each ik. So this is slightly confusing, but so recall that this phi is defined in the previous slide, and this is defined by using the coincidence of fundamental module and affine cuspidal module in under the special choice of strong DI data. And so note that here we take D0, but here we take D. So using the correspondence in the special strong DI data, we rename the affine cuspidal modules. And then now affine cuspidal modules are parameterized by this set. And then we consider the following definition. So for a snake xi, so recall that a snake is a sequence of elements of Jn. And for a snake xi, we denote by SD xi, the head of the tensor product of affine cuspidal modules, whose labels are appearing in xi. So in order to define this, we need to change the labeling. So this is the same with the previous slide. And so note that if we take D0 as a starting strong DI datum, then in this case, affine cuspidal modules are fundamental modules. And moreover, in this case, the head of this tensor product is nothing but the simple module associated with the monomial obtained by taking the product of them. And then this is nothing but the Muhin-Young's snake module. So under special choice, our definition recovers a Muhin-Young's snake module, and so this module is a generalization of Muhin-Young's snake module. And this is the main theorem. So for a prime snake Xi, this short exact sequence holds. And moreover, the first and the third terms are both simple. So these are both simple. And these snakes are the same with those appearing in the Muhin-Young's externality systems. So in particular, if we take D0 as a starting long Duality datum, then our modules are Muhin-Young's snake modules. And so from this short exact sequence, we obtain this relation in the Grothendieck ring. And this is the externality systems. So in this sense, our theorem is a generalization of Muhin-Young's externality systems. And I will give some one example. So let us consider this prime snake. Then our main theorem says that this short exact sequence holds. So if we take this special fundamental modules as a strong Duality datum, then affine cuspidal modules are fundamental modules, and our snake module is the same with Muhin-Young's snake module. And so this theorem recovers the Muhin-Young's externality system. But if we take another strong Duality datum, then in this case, affine cuspidal modules are no longer fundamental modules. And moreover, in this case, this module becomes slightly more complicated. In particular, in this case, the highest monomial of the head is not just the product of those of factors. So in order to see this, we need some calculation. But anyway, we can obtain this simple case. And finally, we in this, if we choose these strong Duality datum, then this short exact sequence is written explicitly in this way. So these are seemingly completely different short exact sequences, but they come from the same one. And I will give some remarks on the main theorem. First, in the previous work of Kashiwara, Kim, O and Park, they proved exact sequences coming from the T systems in general types, or simple modules constructed from strong Duality datum. So for T systems, similar results were already obtained by them. And then from their result, I thought that a similar approach can be applied to the externality systems. And this work is obtained. So their work strongly motivated our present work. And we also generalized Muhin-Young's externality systems of type Bn1. So recall that Muhin and Young also obtained externality systems of type Bn1. And we also generalize this result. And in this type, we use different reduced word, but I will omit the details. Okay, in the remaining 10 minutes or so, I will give a sketch of the proof. And the key lemma is as follows. So in this lemma, we can take arbitrary strong Duality datum and reduced word. So in this lemma, we can take any type of strong Duality datum and any reduced word. And let us consider the associated affine cuspidal modules. Then the following lemma is proved. So for an increasing sequence of integers, we denote by SKST this head of the tensor product of strong affine Casimir modules obtained from a subsequence of K. And we assume these conditions. So these conditions say that the values of delta between a single affine Casimir module and the head of the tensor products are 1 in many cases. Then, under these conditions, we can show that this short exact sequence holds. And moreover, the first and the third terms are both simple. Then, applying this lemma to our setting, we can obtain the main theorem. So, by this lemma, our proof is reduced to the calculation of the values of delta. So the next problem we should consider is how to calculate the values of delta. And it is known that we can obtain values of delta using a crystal theory. So recall that we can define an algebra homomorphism phi d, which maps an element of upper global basis to a simple module. And it is well known that this set of upper global basis has a Kashiwara bicrystal structure. And then the following proposition is known. For a simple module S, defined as the head of the tensor product of affine Casimir modules, the values of delta can be obtained from the values of epsilon I or epsilon I star. And epsilon I or epsilon I star are certain functions appearing in the crystal theory, and the definitions are like this. But anyway, this proposition says that we can calculate the values of delta using the theory of crystals. Actually, when S is a snake module, we can calculate these values in the crystal theory using the Reinecke's algorithm. So I will not give any explanation to Reinecke's algorithm, but this is a very useful algorithm to calculate these values using some combinatorics. Anyway, we can calculate these values for a snake module. And then we can show that they satisfy the conditions of the previous lemma. So namely, we can show that if this sequence gives a prime snake module, they satisfy these conditions. So by this lemma, we can obtain this short exact sequence. And then by analyzing this term in more detail, we can obtain the main theorem. So this is a brief strategy of our proof. Okay, I will stop here. Thank you for your attention.
Are there any questions or comments? Is this the full presentation of the Gotthard grain? Or do you have more relations?
Oh, sorry.
So are these all relations of the Gotthard grain, or do you have more relations apart from these?
Oh, they are only.
Yes.
Sorry. Yeah.
Are these all? Is this a full presentation of the Gotthard grain?
No. So Gotthard ring is commutative, so there are many relations. And so moreover, Gotthard ring has a basis by the simple module, but there are many imaginary modules, and they are quite difficult to treat. And so this relation is just a very small part of relations. Fundamental. So yeah, so So in type BN1, we can show the similar results. And so, this lemma this lemma holds in general case. So if we can find these the modules satisfying this conditions, then we can find modules satisfying this relation. But it is not so easy to find. So far, I can only find these cases.
So when you talk about Reinecke's algorithm, do you mean anti-chains in the Ausländer-Reihenkurve and using that to calculate the epsilon I star, or which algorithm do you mean? Reinecke's algorithm, you mentioned at the final slide of your talk.
Right? Oh, where?
Right. Reinecke's.
Sorry?
Reinecke's algorithm.
Reinecke's algorithm.
Yeah. Is that the one on the Ausländer-Reihenkurve you mean? So you're constructing anti-chains there and then taking the max?
The algorithm is, in some sense, this can apply to very general case, but in order to use Reinecke's algorithm, we have to, first we have to fix a reduced word, and this algorithm can be applied only to adapted reduced word. So in particular, this algorithm can be, so far we can apply this only for these cases. Sorry. So,
no, but I think we can discuss after. But my question was just if you mean by Reinecke's algorithm that this epsilon I can be calculated by some max using anti-chains in the Ausländer, right?
Yeah. That's correct. Yeah.
Okay. Thank you.
There are more questions? So if not, let's thank the speaker.
Thank you very much.